Okay, fine. So this is about muon cooling. I already have prepared some of these stories about 1.5 years ago, when we had a meeting in Venice, this Mila meeting, Mila Baldacciolin, but it wasn't very much appreciated by anybody. Nobody made any comment. Everybody slept through the talk. It was fine. So this is a repetito iuvant, so I'm trying to see whether we can wake up somebody here at this time and understand what to do on these questions. Now, let me say, let's see whether it works, yes. Now, let me start a little bit of physics, and let me tell you the question of metal symmetry breaking in a TeV scale. It has been widely argued by very influential theorists that new physics must necessarily appear at TeV scale. One of the main reasons for arguing the necessity of nearby SUSY. This was based on an argument, which, by the way, is no longer true, that the otherwise divergent self-interaction of the Higgs sector does require a cutoff at a TeV scale. Now, you can see that the situation is plotted from this graph in the other side. I hope everybody can see that, in which you see the mass in GeV. You can see the mass of the threshold, the mass of the limit, and you can see that essentially with the mass of the Higgs, as it turns out to be in this small region, everything is allowed, and there is no need to say that you must have the so-called no-fail theorem, in the sense that you must have supersymmetry necessarily, otherwise the Higgs would be diverging or will not be acceptable, because you can see the mass of 125 GeV that does require, without novelty, a legitimate cutoff all the way to the Planck mass. You can see you can go all the way down to the Planck mass. I mean, see, this thing is working. Yes, you can go all the way to the Planck mass for the lambda, for the cutoff mass, and still be acceptable in this situation. So therefore, the conclusion, there may be only one standard model Higgs to be confirmed experimentally, and no need of the so-called no-fail theorem, no need for symmetry, no need of everything. The Higgs particle is like any other scalar particle, has a property to be this type, and that's the end of the story. Therefore, this kind of no-fail theorem is now end of the story. In fact, I can see very few theorists today that are talking about SUSY. I cannot hear the word SUSY repeated in the whole conference. So things change. Maybe some people may tell you why. But the fact is that the main important question we have ahead of us today is not so much whether SUSY may or may not exist. Let's first see whether they find it and then we decide. But the fact that Higgs is a particle like any others, and it requires to have a story which is as complete as it can be the story of any new major discovery. Now, let me continue to the next transparency here and say, during the last 20 years, the CERN, 20 years, I mean, I wouldn't spend 20 years, my time I would be 100 years old. So, CERN plans to pursue the hadronic production of the Higgs-related sectors and the possible existence of SUSY. That's the kind of program that the CERN intelligentsia is advertising. The existence of additional Higgs particles is assumed to be unlikely within the LHC range. In fact, we know that the number of Higgs now is there is no Higgs all the way up to 600 GeV and maybe more. And therefore, the conclusion is there is just one Higgs at our mass, period, and nothing else for at least half a TeV. Now, therefore, studies will concentrate on the properties of the already discovered mass. This is the real key element. The Higgs luminosity, high luminosity LHC is already a sort of Higgs factory, able to perform relatively accurate, and typically it's about plus or minus 10% measurements. And there's certainly plenty of opportunity to check the coupling, since at 125 standard model Higgs boson has several substantial branching fractions, BB bar, WW, gluon, gamma, and ZZ, CC, etc., which all have to be measured, and God knows whether maybe other factors are there. So there is a huge amount of physics to be done in order to measure in each and every one of those channels the properties with a proper accuracy and see whether, in fact, it's correct. By the way, an interesting factor is the gamma, which is also substancy to the high mass resolution and relatively low background. And this is the future for LHC. Now, in particular, there is a story, which is very similar to the case of Z0. In the Z0 case, we had the hadronic discoveries, U1 and U2, who did this kind of experiments, and they got a result. And then that was a little bit equivalent to what has been done now with the Higgs particle discovery with hadron collisions at LHC. But then there was a second phase. There was a second phase done with the Z0, which allowed to measure the resonance peak at a very high resolution. And therefore, there is a sort of chicken and egg situation, which is the case of W and Z. And it would seem to me that the same kind of argument is required also in the case of the Higgs. And therefore, the need of a specific Higgs-dedicated equivalent thing to the one of the LEP was for Z0 is of particular importance. In particular, like in the case of Z0, the determination of H0 width will be crucial. The width will be crucial to determination of the nature of the particle and the underlying theory, because the width is really measuring the story of everything. If the width is right, then everything is in order, so to speak. And of course, the important thing is standard model prediction. It gives you a Higgs line of 4 MeV, which is also a formidable task, because you're talking about a particle that goes 125 GeV, which is only 4 MeV wide. And therefore, the underlying study of that thing is totally different than the one you would have if you had, for instance, the case of Z0, a 2.3 GeV mass to play with. And you can see here the peak. Here is the peak, the bright-Widgren peak indicated there. And even 1 MeV Gaussian is already making an effect. Here you can see the graphs there. The 3 MeV line is in there. The 5 MeV line is there. And you can see that even 7 MeV line is down there. So even a rather small multiple scattering, if you like, a Braid-Wigner addition to the line will really substantially change the value of the mass. Therefore, you have to know that the number extremely well. This is an absolutely substantial, formidable task to carry out this problem. But it has to be done somehow. And now here you can see cross-section convoluted with Gaussian beam distributions. Signal is not affected only if the RMS beams energy width is only a few MeV. Otherwise, the width will be lost, and will not have no width. You'll not be able to do the equivalent of what you did already with the Z0. Now, what precision is needed in order to search for possible additional deviation from the standard model? Under the assumptions, we have one Higgs particle to understand, to discover, to study, and that's it, as is most likely the case. Now, there are, of course, a number of theories which have an enormous amount of exotic alternatives and changes, and those are used as an argument to decide whether Higgs is really what we think it is or something else. Now, let me show you here some example here of some theories. They mix in singlet, composite Higgs, minimal supersymmetry, and so forth and so on. And you can see the difference of the line indicated there in these TT bar, VV bar, BB bar. These are the numbers which have the changes you can see. And you can see essentially that these are the ultimate LHC predictions from the experiments of these particular channels, assuming that you are going to have the high luminosity LHC, you're going to be able to collect an incredible number of events of the order. This is measured to the 42 square centimeter. And now if you collect the 10 to the 42 centimeter square cross-section, these are the numbers which now they believe they can get. And these are the theoretical typical predictions of numbers. These are the accurate or systematic, if you like, this is a standard deviation you expect. Now, you can see here some of the possible alternatives indicated there for SUSY, composite Higgs, top partners, etc. This is all theoretical thinking. But anyway, the conclusion is that sensitivity to TeV new physics, and we want a 5 sigma discovery, requires an experimental percent or sub-percent accuracy on the rates. And therefore, you have to make a detector which is capable of measuring, say, the number with 1% standard deviation, so that the 5% effect, which is a typical effect that any change of theory will give you, will be a convincing 5 standard deviation story. So that's the kind of situation we are. Now, that is the title, therefore, my presentation, the Higgs particle after the CERN LHC or beyond the CERN LHC is a possibility. Now, studying the Higgs beyond the LHC, there is certainly could be convinced that the scale sector is definitely one of the keys to the future understanding of elementary particles. As I say, after P discovered that the zero-detail studies Laplace lacked in very clean conditions, have been a necessary second phase, effective lab second phase. A similar second phase may also be necessary for the C0. This is what is the basic argument, justification for what we're talking about. In the case of H0, it will be necessary to produce a very large number of events per year in very clean experimental conditions. And there are two possible alternatives which are around, which I like to discuss, which I like to describe to you. One possibility is the E plus E minus collider. At 10 to the 34 luminosity, let me tell you that the luminosity of the LEP was 10 to the 32, so we are talking about 2 or 3 orders of magnitude higher luminosity than the best luminosity LEP has been able to measure at the Z0 peak. In this particular, you will not produce the Higgs alone, because the Higgs cannot be associated to electron positrons, because any scalar particle has the mass squared coming out of the Dirac equation, and therefore the circumference of the has to measure the Z0 plus you have to measure that 0 plus Higgs signal, and this is 200 femtobarn, and the conference of the new lab ring is about 80 to 100 kilometers, and we'll discuss that the possibility. As you can see, a lot of people are talking about a 100 kilometers machine, which can do that. Repeat, 100 times the luminosity of LEP, and 100 kilometers circumference to do this. The second possibility, which is the purpose of my discussion there, which is somehow almost forgotten alternative of a muon collider. In the case of muon collider, we are on the peak, and the signal is not 200 femtobarn, but it's rather 20,000 femtobarn on the resonance if the beam is narrower, because you're right on the peak, like it is a zero case. And in S states, the collider radius is only 50 meters in diameter, in radius, and the luminosity is only 10 to the 32, so you gain a factor between 200 femtobarn, 20,000 femtobarn, is a factor 1,000 here. So I've used 2 orders of magnitude, but in reality, the 3 orders of magnitude, which is 20,000 to 200 femtobarn, to measure these things. That is the second alternative that you have to see. But the collider radius is much smaller, 50 meters, but of course, novelty is required. You have to be intelligent and to create muon cooling. And this brings about the story of muon cooling, to which there is a preliminary story to which I have been rather central, which is a question of the anti-proton cooling. Let me tell you right away that the muon cooling is much easier than the anti-proton cooling. It's much more difficult to collide and accumulate antiprotons and collide them than accumulating muons and collide them. Anyway, that's it. Now, let me show you here this first option. There is a huge E plus rings, and the option of circular Higgs factories are very popular around the world. I've indicated here all those gentlemen, ladies and gentlemen, which come proposing this kind of experiment. You can see all these places are places. Here is Fermilab, this is Lab 3. There is here West Coast, somebody's talked about. Here it is CERN, and we'll discuss in a minute. Some Russians want to do something, some Japanese want to do something, and now there is also some Chinese in there, I guess in this list, also visible there. This is a Chinese story. All these people want to build a Higgs factory using essentially a Z0 plus Higgs object with 250 GeV beam. Let me try to understand. Now, this is a typical example. This is the same example of Super Tristan. Tristan, 80 kilometers circumference range, 12 kilometers length. Here, the diameter is just equal to the LHC size. And you can see here where it is in Japan. Here, now coming back to a more popular situation. This is the situation of CERN, which is highly supported by the present CERN management. There is the director for research who has given 1 hour-long talk on this story, and everybody seems to be to talk about the reality. And now you can see here, this is the baby ring, which is only LHC up there. And you can see what you have to do. First of all, you have to cross the bay. Everybody knows that crossing the bay for Geneva has been a story we've been talked about the last 50 years, politically and so forth and so on. Now they are going to say that instead of solving a thing for public applications, you have to just to do it in order to be able to carry around. CERN can do it for them. And then it goes on, this SLF is here. You have to go beyond this SLF, go around in this circle and so forth. This is the kind of project which is being presented. And it's being described by all these gentlemen, and is now becoming a story. Now, knowing that the size of an accelerator is proportional, presumably, to the size, never mind the fact that to go under the water of the Lake of Geneva and so forth and so on, things like that, it's quite clear that the cost of a ring is proportional to the size. So maybe you could say that this is maybe 4 or 5 times the cost of LHC, of a LEP ring. So you know what we're talking about. Who the hell is going to find that money? That's none of my problem. Now, let me continue here. Now, the real question is, what are the requirements? Now, as I said to you, in order to do the experiment, you need at least 100, probably 1,000 times the luminosity of LEP. And therefore, the luminosity has to be pushed to the Brimström limit. We have a lot of people here, like you people, which know I've tried to discuss that. In fact, you can see what we're talking about at the collision at an angle, but if you're bunches, the B factory story has been a very popular story at Frascati, so you can use that as a reference. Now, the B factory is a 5 GeV machine. Here we are talking about 250 GeV machine. Now, you know the scale and the dimensions of the system. I also know that the B factory, what was it? $500 million or something, euro or something like that. So, what? Somewhere between half and 1 billion. And here we are talking about 50 times the size of the system, of the machine. So, you know that we are not talking about peanuts. And now, this is the main argument. The argument is very similar to that thing, so you know everything about it. The luminosity, now the luminosity is few times 10 to 34. Cost and power consumption is about 100 megawatts of beam power in the system, of the order comparable to around a linear collider. In order to reach a luminosity factor 1,000 times LEP2, a power consumption 5 times the one on LEP2, the two main cures are one big ring, huge ring, 80 kilometers for super Tristan TLEP, extremely small vertical emittance. Now, the vertical emittance of LEP has been 3 microns. Here we are talking about a beam of 0.01 micron. So we are talking about beams which have the size of 100th of a micron hitting another beam coming from 80 kilometers away, and the two things are matching each other within 100th of a micron. Now, and I believe, allow me to say that at least to my old-fashioned point of view, you could say the performance is border of feasibility. So this is what we are talking about if you want to do that experiment. And that experiment will not be able to measure the Higgs mass per se, because the Higgs mass cannot be measured by measuring only Z0 plus Higgs, because the mass resolution is not. However, the mass width of 4 MeV cannot be detected with all that kind of stuff. So there is a lot of people talking about this thing, and now it's fine. I don't know how serious those people are, but as I say, cost of a machine proportional to length. This is, we're talking about 5 times the cost of the present LHC LEP ring and the corresponding factors now and so forth and so on. Now, the two choices are here, and they are comparable. You can see here, taken from the paper from the Japanese. Here you can see the construction costs in various energies, the rings and linear, and you see the power consumptions of the ring and linear. You can see the amount of consumption of power is similar to the linear, and the cost is similar to a linear. See, the two things are within a present noise level, just comparable. So therefore, the choice is between linear collider, circular ring, and comparable cost and power consumption. The more conservative ring is preferred, because to make a brand new linear collider of this magnitude requires an additional conditions and no extra advantage, because costs are comparable and results are the same type of factor. So that's what it is. Good. So there we are with the story. Now let's continue. Now, the second option, which is a sort of hidden option, nobody seems to be talking about at the present moment, is the muon collider. The direct H0 cross-section greatly enhances the mu-mu collider when compared with the plus and minus collider, since the S-channel coupling to a scalar is proportional to the lepton mass squared. Now, like in the well-known case of Z0 production, the Higgs scalar production and S states offer conditions of uniqueness where nobody would agree with that statement. A unique feature of such a process, if a property of luminosity, is its actual mass, its very narrow width, and most decay channels can be directly measured and with accuracy, because you are in clean, proper conditions. Therefore, the property of the Higgs boson can be detailed over a larger fraction of a model parameter space than any other proposed accelerator method. That is a very important statement I'd like to underline. An particularly important conclusion is that there will have greater potential for distinguish between a standard model and a standard model like H0 of SUSY or any other new collider. If there is a SUSY around even above the mass of the Higgs or above the mass of what you're talking about, there will be consequences coming because of virtual graphs, and therefore the precursor sign of any like SUSY may come up and show up even earlier than at the lower masses than SUSY. So therefore, this is something, if you find exact agreement with the theory, that's a strong argument against having SUSY around, if you still believe in that. Now, let me show you here some of the graph, the situation. I put a red line, the characteristic line, which corresponds to the mass of the Higgs. You can see here two things. You can see here to the left the signal of a BB bar channel, for instance, and the background. You can see they are quite comparable. In there, even in the BB bar channel. Of course, in the case of other channel, for instance, in WW pairs, is a clean, super clean signal because the WW and other channels are much lower. But even in the BB bar, the hadronic signal, they are comparable in size. And there it is. And you also see the various decay channels are indicated there, the gamma gamma, all the other channels you see marked in a clear way. You can see by yourself what we're talking about. Now, the muon collider with underground muon cooling and the luminosity is only 10 to the 32, which is the order of magnitude of what has been already done with the P bar P at Fermilab. For instance, what did you have? 10 to 31 was the typical luminosity you get. So we're talking about luminosity, same order of magnitude. Decay electron, there is one problem here which has to be underlined. Decay electrons. Because there are a large number of muons will give you a large number of electrons, so therefore there will be a lot of synchrotron radiation which is going to be emitted, and there will be a certain number of decays, which has to be confronted with the actual results, so you have to be very careful when you design this all concentrated. This is one technical problem. And then now the very narrow resonance signal, which is about few parts in 10 to the minus 5. The width of the mass of the muon is 3.6 10 to the 5. For standard model, we don't know all over the most non-resonance backgrounds, and therefore you have clean conditions, but very demanding conditions from the point of view that especially the mu decaying to the electron will give a lot of electrons, not that many, they're about 10 to the 6, 1 million electrons per meter at 20 GeV emitted around. They're all collimated in the forward direction, but you have to worry about it. So the synchrotron radiation phenomena, a certain important phenomenon. Now, cooling with non-Liouville particle accelerator, that's the reason of the argument. Already in Mura in the 50s, it was realized that some beam phase-space compression may be often necessary from the source to the collision point. That was already O'Neill, was Piccioni, Orestes Piccioni, Simons were doing that. And of course, the real key is Liouville theorem, which gives you a very important condition that anytime you have an Hamiltonian, anytime you have a force derivable for a potential, then the six-dimensional phase space is preserved, well, at best, without, if there's no paired losses. So at best, you make dV equal dt equals 0. So if you have very big phase space to start with, you cannot compress it because Liouville theorem will not allow you to do that. Therefore, we need some kind of dissipative, non-Liouvillean drag force working against the particle speed and not derived from Hamiltonian. These are the conditions which impose for cooling. And there are several alternatives. Synchrotron radiation, everybody of you knows that, but it's only good for electron and positrons. Electron cooling, the electron beam both traveling with speed equal to the one of circulating beam. This was Butker ideas and the one which also used for P bar P. Stochastic cooling, where it works on a small amount of particles, statistical fluctuations, and this is Van der Meer story. And the other, now we're talking about our own equation, ionization cooling, when DEX losses are lost to the beam. With any of such method, and we accelerating cavity replacing the losses, one can compress the space volume, and this is the kind of thing we're talking about. And then we go to the next step, which is from antiproton to muons. Cooling is essential whenever secondary particle produced from initial collision lets the accelerator, for instance, to be accumulated in storage rings. And well known in the case of one antiprotons, both stochastic and electrocooling has been vastly used. PP-bar correlation have permitted the discovery of the W and Z, and allow me to say, Giorgio, also the top, I hope you remember that. And initial ionization cooling is specific of muons, and since there are many on electromagnetic interaction, since there is interaction with matter, the muon lifetime may be long enough to offer, with the help of cooling, a reasonable number of mu plus mu minus collisions with a collider, at the X resonance in the S state at a very low energy, 62 GeV per beam, which is it's a perfectly legitimate normal energy to any possible activities. Of course, this idea has been discussed already by Butker in the 60s and by Skrinsky in the 70s. Comprehensive analysis has been given, for instance, for the 90s, Neufer in the 90s. And since the 90s, not much has been really happening on this subject. So let me mention here, for instance, one important contribution. Neufer has done that. This is particle accelerator of 1983, and this is the main paper which we're starting from. Now, what is ionization cooling? Ionization cooling is called DX cooling, closely resembles to synchrotron compression or relativistic electrons, with a multiple energy loss in a thin Z absorber substituting synchrotron light. So you don't have synchrotron light, but you put an absorber, it does the same job. The main feature of the method is that it produces an extremely fast cooling compared to other traditional methods, and of course this is a necessity in the case of muons. Transverse Metatron oscillation are cooled by a target foil, typically a fraction of gram per square centimeter thick, milligram per square centimeter per turn are sufficient. An accelerating cavity is continuously replacing the momentum. As you do with synchrotron radiation, you take away the radiated energy and you replace with clean energy, the clean energy being generated by the accelerating cavities, and that, of course, reduces fluctuations and losses. Now, unfortunately, for slow muons, the specific DDX losses are increasing with decreasing momentum, which is not the case of synchrotron radiation, where the faster electrons are radiating more than the slow electrons. In order to cool all the longitudinally, chromaticity has to be introduced with a wedge-shaped DDX foil in order to increase the ionization losses of faster particle. So your wedge has to be, your cooler has to be a wedge, so that the particles which are going at the periphery of your ring, which they have to go to a much longer average radius, they have to ionize more, because that has to compensate the structural behavior with the energy which is known to be in the correct direction. Now, early cooling scenarios have been done in the 90s, with a single-pass linear collider, in which a large number of RFDs restore the energy lost by the low Z absorber, for instance, any in ionization cooling. However, although a single-pass linear collider was done mostly, also some cooling rings were also observed. And for instance, there is one experiment which has been going on for the last 20 years, which is called MICE, which is a sort of an idea in that direction, but it's not the kind of thing I'm trying to propose here, because I'm much more ambitious than what this gentleman from MICE want to do. This is the piece of paper coming from Palmer, and it's called the Guggenheim channel. You can see what those people are talking about. You make a channel like this, the muons come in wide and in width, and then they are decelerated at the end, the energy lost with an absorber, they get reduced. But also, cooling rings were discussed, and this is the MICE detector, which is a linear piece. You can see here, which is under construction since a number of years. There are two RF cavities to get energy. There is dumping, there is absorber to lose it, and the effect is quite small. In this kind of device, you get about 20% reduction in emittance of all this machine. We are talking about a 10 to the 6th factor in our case, so this is a long way off from what it is needed. Now, over the last significance, there's been, however, a very significant process in developing concept technology needed to produce, capture, and cool, accelerate 10 to the 11 muons per year. And as I said, the extensive study has been performed about 20 years in the US, and very much discussed internationally. And three different possible alternatives were described at that time. One was a 3 TeV collider at 10 to the 34, a 600 GeV collider, a Higgs factory. At that time, we did not know what the mass of Higgs was, but we knew there was about 110 GeV coming from the prediction from LEP, actually. And the neutrino factory, also another important question which I'd like to take about. And one of the important things, cooling muons means muons are colder. If the colder muon also give you colder neutrinos, and therefore there's not only a benefit in doing collision, but it's also a very important benefit in making long-distance neutrino factories in which the cooling is reducing the size of the beam, and therefore you get a higher signal, even with a given detector, even with the same conditions. So it's another important issue which is worth looking. Now, of course, as I said, the recent discoveries of the Higgs particle and the observation of sine theta 1,3 neutrino oscillation, this is another important result, mechanism have strongly revived the interest in these studies. So both neutrinos and Higgs factory are becoming now an important subject. And now here I have a whole line of papers. You can see all these are the people which have done a very nice work on this, which is worth mentioning. And you can see here a number of alternatives. And you see comprehensive technical reports have been done, but all those reports are essentially to the way now have a history, belong to history rather to the active activities, because as far as I know, at Fermilab, there's not much activities today is going on. There is a lot of dreams, lots of activities, but some necessity of going on with this problem worldwide is justified. So let me get the next step, experimental realization of initial cooling experiments to ensure the full 6D cooling of muon by a factor of 10 to the 6. And this is the next step we are discussing about. The initial cooling experiment simulates very much the mimics of what we did already for the P-by-P collider. As you remember, the P-by-P collider was possible because initially we did an experiment by cooling antiprotons at the PS. Petrucci, by the way, was the person in charge of these activities, and that created the landscape and demonstrated the feasibility of the system, which created a possibility of building and after the antiproton cooling ring, which was the final result, and the antiproton collision. Here we are talking about something similar. We're talking about a simple experiment, a 10 million euro story, which allows you to get going into this project and gives all the underlying physics understood, and then after that you're convinced that thing can be done. Then after that you start talking about generating conventional facilities and all this and the other to do it. And for that, you don't need to have a very high number of pions, because a handful of muons are sufficient, because individual muons have to be cooled by the system, and you have to look at that emissions and demonstrate that the cooling is taking place as a factor 100 vertical, a factor 100 radially, a factor 100 in momentum loss. Now, next step. Physical requirement to study already underlying muon cooling suggests a specific program could be a practical realization of full-scale cooling demonstrator capable of the full capability in 3 dimensions. This corresponds to the realization of a cascade on conventional but very small rings of few meters radius. They will sit in this room here, in front, in this hall, just in front here. In order to achieve the theoretically expected longitudinal transversal emittance with asymptotically cooled muons. In order to demonstrate this initial cooling experiment, muon may be produced with existing accelerator at low intensity, any PS, any place in Zurich, any place in Brookhaven, in CERN, or in Fermilab, anywhere can do it. In fact, you can even presumably find a handful of muon, even a Frascati, if you insist in some kind of a way, produce them with electrons. Another conventional facility, namely the high-intensity proton accelerator, the pion muon production target, the sub-second muon accelerator, and the accumulation and storage ring may be constructed later and only after the success of the initial cooling experiment has been confirmed. And these are all conventional facilities. You know, every one of those things is well known. Everybody knows how to do it. So the only real question mark is, can you cool a muon? After you have that, everything else is trivial. And trivial, I mean. It can be done using existing resources and facilities which are within the realm of activity of an ordinary experiment. Now, the emittance, now let me say about the muon cooling. The muon cooling has some formula, which I now briefly mentioned to you, and they are being initially discussed in the 90s by Neufer, and now they are being used also by others. And there you can see that in the transverse emittance, you have 2 numbers. You have the epsilon dz, which is the loss per unit of time of linear path of the emittance, has a term which is a cooling and a term which is a scattering. And the 2 terms have to average to 0. The beta cross-section is indicated there, additional length is indicated there, and additional losses there. The cooling process will continue until an equilibrium transverse emittance has been reached, which is given by such a formula. You can see there what is the equilibrium cooling, when the cooling and the heating balance themselves. The equilibrium emittance En, and it's invariant En divided beta gamma. Invariant emittance, what really interests us, because we want to accelerate it later on, is a function of momentum. You can see here the graph here, which is a very important graph, which I like to spend a little time in discussing. You can see here the transverse emittance in milliradian in there. And you can see here the muon momentum in MeV over C from 50, this is a MeV, 50 MeV to 250 MeV. You can see here the actual emittance, but what really interested is the invariant emittance, and you can see the invariant emittance is essentially flat. So you can do it at the proper energy, and you have plenty of space in between the two. And now for hydrogen cooling, beta star 10 centimeters, which is a cooling place where you do things. And these are the number from, it's essentially less than 700 millimeter milliradian. A millimeter milliradian, or 10 to the minus 6 radian meter, is a typical number used for accelerator numbers. Everybody knows that number. And this is about between 700 of this number. And, sorry, excuse me, what happens here? Disaster, sorry. And this is the kind of thing, that means that if you take that beam transversely, and you go to a collider point at 125 GeV, after you go through all this transformation of William way, at the end of the day, you will find the bunch equilibrium will have a transverse size of 240 microns. There's not a 100th of a micron of electron-positron rings. It's 100 microns, 250 microns, a quarter of a millimeter in size for the collision point, with a beta of 5 centimeters, which is typical beta you have in a proton and in a collider focusing place. So these are the kind of numbers you're dealing with. So this is pretty good. I mean, 5 centimeter beta, and these numbers are possible with this kind of conditions. So that cooling works. Now let's look at the other longitudinal cooling. Longitudinal cooling is it's of course balancing, and there are 3 elements there: the intrinsic energy loss, the wedge-shaped absorber, which we need in order to get the effect, because longitudinal, as I say, remember, you have to reverse the direction of that sign, and the struggling, coming from DDX losses, you have struggling in the ionization losses, and the balance with interesting numbers. I give you the numbers here, and these things is pretty clearly explained in this number: chromatic dispersion of the absorber, and so forth and so on. All that is perfectly obvious. I think you can look at it, and you can see what the answer is. The thickness of the absorber must be varied with transverse position to produce a process energy dependence. It decreases the energy spread, is what I explained. You have to compensate for the fact that a slower muon should lose less energy. Energy cooling will also reduce transverse cooling. And remember, there is everybody here in this room knows what the Robinson law is. The number of the 3 component has to be 3. There's the famous Robinson conditions. I mean, the experts know that, and the damping element, so there is a connection between transverse and longitudinal cooling coming on that. Anyway, the equilibrium, energy equilibrium is given by this formula, and that is important is the graph you see there. You can see again the muon momentum, and you see another thing, the RMS equivalent. This is not flat. This is a logarithmic paper. You can see it's changing very rapidly. At 250, you can get about 10 MeV of RMS width, that's it. But if you go down and you go to 100 MeV, you can go less than 1. So there's a very strong, significant difference between the angle, fast dependent from transverse P mu. At 250 MeV, the delta RMS is 10 MeV. At 85 MeV, it's 1 MeV. So it's an order of magnitude gain going from 250 MeV over C to 85 MeV over C. Now it turns out 85 MeV over C, you don't have muon to start with, because the cross-section for pi, cross-section and so forth, as you'll see, peak to a few hundred MeV. To make a 85 MeV over C muon, it takes quite a few muons. At 50 MeV, you will get even better. You get only 0.35 MeV of the effect. So there is a very strong dependence. Okay. Optimal muon producing momentum, the energy spread is too wide for the H0 width. The H0 width, as you remember, has to be less than 4 MeV in order to be able to be successful. If you have 10 MeV to start with the RMS, by the time you go through all those things, you get yourself in trouble. So this is the key element. You got to go and be able to do things in such a way that longitudinally you're in much better shape. Now, single sign cooling arrangement in 2 rings. Now, therefore, 2 rings are needed, either a few particles, and this is what you're proposing. Initial cooling experiment I'm advertising to you is very clearly shown here. Pion become muons. Muon go to a cooling ring, which is optimal for the collection muon momentum, which is over 250 MeV. Then you go through a next step, decay channel. Then you go to a low beta channel in which the pre-cooled muons are slowed down, DDX, Liouville's cooling. You put DDX, and the DDX is reducing the momentum to something like 80 MeV. And then you got the second cooling ring at 80 MeV, which is there. I put it smaller, but could be also the same size as the previous one. And then you kick it out, and then you get at the end a 6D analysis of decay muons. So that is the initial cooling experiment you have to construct. Throw a bunch of muons in there, cool them first, move them into the shift in energy, make a second coolant, and then look for each and every muon, the angle and the momentum with the spectrometer, and measure that and demonstrate that you get the 6D analysis of decay muon, which is a factor of 1,000,000 to start with. And this is possible, but you have to be demonstrated. So you take 1 muon at a time, and you measure the spectrum, you plot the spectrum, and you demonstrate. It reminds me quite a bit ADA's story with Touschek, since we are all talking about Touschek's story. Here, make something which really gives you the idea of what you're really doing. Now, okay, now, the first wide beam going to collect the widest muon momentum around of 200 to 400 MeV, and take a first major reduction in transversal longitudinal emittances, but still with delta RMS of about 10 MeV. Now, you need to have solenoids instead of quadrupoles. That's the first condition, which allows you to remember, quadruple is only taking a second-order effect to delta P, while solenoid is first order. There are few turns to do, so no higher resonance. This is a pseudo-ring, because you only do it, only integer resonance are giving you trouble. The other high-order resonance, you're not producing anything. Now, the first cooler initial sorbate does not have to be made out of liquid hydrogen, but you can use a solid material, because after all, you're going to cool it later. And so you can do any material which does it. Now, an intermediate liquid hydrogen absorber is a piece of 3 meters long of hydrogen, 3 meters long hydrogen liquid in a low beta channel. You put some magnetic field to keep a low beta, and it reduces the momentum by range. And then you collect it out. The result beam will then be extracted, and its momentum reduced to about 50 to 80 MeV over C. And then the second deep freezer cooling must be adequate, struggling to well below 1 MeV, so that you have a chance to get the Higgs story, which is sensible. Now, there are examples of this cooling ring. For instance, this is a cooling ring put together by Baldwin and Packer. This is not what you're going to do. I mean, this is a kind of sort of quasi-theoretical story. You can see average momentum is 200 MeV, diameter 10 meters. So we are talking about a 10-meter diameter unit that we are talking about. This is the kind of thing we really need to worry about. And you can see here how the thing goes. And in fact, not surprising to see from the right that these are the numbers, circumference, and so forth, all the numbers are indicated there. You can see that as a function of the length of the rotation, you can see here those curves here, the cooling is acting. This is, of course, theoretical. This is a Monte Carlo calculation. I'm sorry, excuse me. These are Monte Carlo calculations and so forth. Now, come back. Here, this is a Monte Carlo calculation which show here how it goes. I mean, it's quite clear that you can see that the thing is cooling very rapidly. As a function, the ratio here is 1 over 302, not in logarithmic paper, due to the cooling and so forth and so on. This is the kind of theoretical story which we have. Let me skip this one. Let me also tell you that I have a time to present you a much easier ring, which I prepared to this, but I will not discuss it now because I want to give you the general fact, but you should be convinced that this kind of ring is perfectly legitimate ring you can do in a proper way. If you want, I can certify that. Now let's go to, since the time is getting short, initial cooling experiment with millimole of cooled muons. Do you have some water here? I have to get some there. Just a moment. Sorry. Scusa, che prendiamo una cosa così, se no comincio a tossire. Non ci sentiamo, scusa. Grazie, ok. So let me continue on this story. From the initial cooling experiment to a millimole cool muons, that will be the next step. Let us assume that you succeeded in cooling this bloody thing by a factor of 10 to the 6 with that kind of tabletop story. Then, by the way, in the case of P bar P, that took less than 3 years. I suppose this is the kind of number we should also assume in this way. You just build it, put it together. If everything works, you have the answer. If you don't, then you have a problem. Now, then you go to the initial cooling experiment, you go to the final system, which I describe here in more detail. The final system cooling experiment is made out of two possibilities. You have a primary ring, you start here with a horn, target horn, mu plus go this way, mu minus go that way. You have two cooling rings, then you have two coolant, and then you have two second cooling ring, and then you come out. And now the bunch length at the end is, of course, delta P is 1 MeV over C, and that bunch length is about plus minus 0.4 meters. But if you really feel that you want to do this thing right, you can use something which is similar to what done in the PS booster. People which know PS booster know that there are 4 rings, one on top of the other, which are operating as a stack. You can make it, if you really want, you can make a stack of cooling rings here and there. Notice that the amount of luminosity goes like a square of the number of particles because it's proportional to the number of mu pluses and the number of mu minus, and you do both. So if you put the 2 cooling rings, you get a factor 4 of the final luminosity. If you have 4 cooling rings, you'll get a factor 16, so in order of magnitude. So there is plenty of room to do that. You can take different species of the spectrum of muon, as you'll see in a minute, and cool them out for, as you'll see in a minute, with Uvillian cooling first, and then put them into a stack of rings, if you really, but I don't think it's necessary. I think 1 ring is plenty good. Sempre il momento Windows match 2 rings with EDX before, and then you do that. Anyway, so let me say, what is the outcome of this? Now, this is the story which is coming from the various phenomena. Here there are 2 possible possibilities here, which are, one is the multi-TV muon collider, and the second one is the Higgs factory. You see, these are the numbers Mr. Skrinsky has done many years ago, these things and so forth. You can see what we're talking about here. We're talking about here of a starting down this way and cooling it down all the way down here. But then here you can see here that in this situation, in the Higgs factory, you still have a delta P over P is much too large, and therefore you have to do it, et cetera. While in the case of multi-TV muon collider, you can have a large momentum spread, and the equilibrium emitters are too large and transversely to longitudinally, and you can do some kind of final system. So all the way to here is common. If you go down to the Higgs factory, you go that way, B. If you go to the multi-TV collider, you go there. In a multi-TV collider, you will have to change the longitudinal and equilibrium emitters a little bit better. But I think I will continue on this and give you the story. Let's get the numbers are. Now, first of all, let me show you how we get the numbers for the final detector. That how much proton energy are we talking about? We are talking about here about, we're talking here about the 5 GeV, 5 megawatts power, out of a 15 to 50 pulses per second machine. So it's fast. It's like the Fermi booster, 15 G per second, but it's done in this way. This is the energy from 2 GeV all the way up to 20 GeV. The repetition rate is 15 counts per second. There's the number of proton per pulses. And these are the muons following up. This is a spectrum of muons. You can see how it goes. You have a stripper here. You have you'll do after you demonstrate the initial cooling experiment as being a success. Now you get it with a system similar to the European spallation source procedure. There's a kicker here. There's a target, and you separate the mu plus and mu minus. You see here the spectra. These are the spectra of particles in momentum. And they are really flat all the way from down here to down there. So it's a big, wide spectrum that you can use. This is a 2 GeV case, and this is the 8 to GeV above. You can see that from 2 to 8, you lose a factor 2 in In rate, of course, you have the same total power, and all these lines are the same because the power being the same, you reduce the intensity of high energy, and the two things almost exactly compensate each other above a certain value. So we're talking about a 5 megawatt average, not peak, average 5 megawatts power system in this particular case. You have proton per pulse, you have a repetition rate. Proton per pulse is about 10 to the 14 proton per pulse in here coming. And the total number of proton per pulse is this number with 15 cycles. If you go higher, it can be better. This is 15. I use 15 because it's the case of the booster from Fermilab. And this is the numbers you get. Now, this is 10 to the 14. Now, this is about a factor of 20 higher than the PS booster, but it's the order of magnitude, not so much a more reasonable number, but it's something within feasibility factors. Then you go from pion and you get to muons, and in doing this, you need you have to use essentially a strong field. So you have to make a 20 Tesla solenoid, secondary particles about 100 milliamp of axis, and the Merit CERN experiment successfully already demonstrated the possibility of producing 15 Tesla solenoids, and actually symmetric solenoid following the Bush theorem, and particle position focused that they can later separate magnetically. By reducing the field, the rotational motion is converted longitudinal to the mode. So you start with 150 MeV transverse from the productions, but after you go through this Bush theorem and all the rest, you got about 30 MeV. You see here the numbers relative to the situations. You see what we are talking about, normalized emittance, which is quite reasonable. And those are the numbers which can be used in order to get the cooling through this line. We can discuss later more detail. And now, after that, you can matching the cooling ring to the proton ring. This is what you might be able to compress or create a booster system with more sort of a stack of rings or reduce the momentum. And clearly here, what you're interested in is in reducing the momentum spread. So you might also put in there a sort of a initial Liouvillean compression with the DDX compensating wedge if you really feel like you want to get some additional things. So you do essentially you have two magnets, so they beam do like this. This is it's compensating, so here you have large delta P and low emittance. Here the delta P becomes low and the emittance becomes large. This is something which you can try to use if you really want to do a better job. It's all details which can be discussed. Now, after that, you can go to after that you fully cool muons to the final storage ring. It's shown in here. You have the injector, the pre-injector. You go to the multiple recirculating beam. You put a cavity here, which picks up a certain field. For instance, here is an example. Here is a momentum spread in which you take you accelerate it recirculating with a recirculating linac. You have here different, the beam comes in here, accelerator comes back again, and then it goes up again to the next ring and so forth. So many times going through the same system, you can go essentially progressively rising the energy from all the way up to MH equal 2 with the help of series several recirculating linacs. And this is the beam of 62 JeV, and this is the pre-injector. This is, some few GeV accelerator. Depends how many rings you're doing. Let me tell you that this is, in the case of LEP, we already had 3 GeV acceleration done with electrons. Here we're talking about similar numbers. So that's all perfectly well understood. I understood that to get high gradient acceleration is one of your dreams also at Frascati. So this is the kind of thing we're talking about. And it's a story, we go on with it. Now let me continue. Now, then for that, then you go and you collide. And this is the typical low beta structure with a high beam going up to about 1 kilometer and then down to about 5 centimeter cross sections. And these are the two totally typical numbers that you're talking about. And this is done with sort of a standard process. The P by P, we did the same. Now, that essentially, what are the numbers here? The asymptotic cooled muon bunches opposite sign collide in 2 low beta interaction points with beta star 5 centimeters and free length of about 10 meters. where the two detectors are located. Remember, this is a small energy machine. We are not building here LHC, we're building a lab-type detector because the energy is much lower and the simplicity is much easier. The bunch traverse size is 0.2 millimeters. The mu tool shift is 0.86, which is a fairly large tune shift, but still it's quite okay if you only have such a short time as you do of a muon, which only lasts a millisecond. The luminosity is about 10 to the 32, and this is obtained with these numbers. There, if I put here the numbers, I get 4.4 10 to the VS, higher rate of possible stacking colliding rings or doing some kind of additional thing. Those are indicative numbers. If you see the numbers here with care, you can read the thing. You can see this is the BB intrinsic. I mean, all those numbers are available to all you if you want to spend some time to look at it. The luminosity is about 0.6 10 to the 32, can be ordered 10 to the 32, so it's quite reasonable. So all that is, in my view, is perfectly normal. The radius of this machine is about, the radius is 50 meters. Let me tell you that PS radius is 100 meters. So it's half the size of the CERN PS. So it's a very tiny object which can be put together. So let me say, 12 o'clock, I have to finish my presentation. So let me show you what it is. So conclusions. The recent discovery of the Higgs particle 125 GeV at CERN has highlighted the unique features of the direct production of H0 scalar in the S state, in analogy with two steps of the Z0 with the P by P and lab programs, and where the mass, total, the partial width, and the H0 can be directly measured with remarkable accuracy and a very large number of events. High-energy mu collider is the only possible circular high-energy lepton-Higgs collider can be easily situated within existing CERN FNL facility. If you want to do the linear collider, which is the idea of the present CERN management, then you have to build 100 kilometers, 80 kilometers ring, and very complicated. Here we are talking about 50-meter radius ring to start with, and it can be perfectly found, arranged into the PS ring, into the CERN, or eventually Fermilab sites. The first step would be practical experimental realization, as I said, of cooling demonstrator, a relatively modest low-cost system, capable of conclusively demonstrate ionization cooling at the level required for a Higgs factory, eventually as a premise for a subsequent multi-TeV collider, and, as I said, for and/or a long-distance neutrino factory. The fuel realization of this muon factory requires essentially two major steps. The 6D phase compression to specify the amount 10 to the 6 based on demonstration of the initial cooling experiment with a chain of very tiny warm rings, followed by the production and collection of millimole of muons for appropriate high-intensity proton accelerator. 5 megawatts proton power is emitted in 10 or 15 or 50 pulses. Acceleration accumulation of the appropriate cooling ring is 62.6 GeV, which is a very reasonable energy. The luminosity can be further increased by constructing a stack of several superimposed PS booster-like cooling rings, where different pi momentum windows, you shift it with putting DDX to get them to the same momentum before they get into each one separate rings, and then you cool them out and you collect them together. Let me remind you the luminosity goes like n squared. The conventional facility to realize the full facility should be constructed only after this initial cooling experiment is conclusively demonstrated, eventually at a different location. Thank you.